Yeah. AT and another one D and C. And I start selling the nuggets, reading all this crazy stuff.
It's very different from your friend.
This is X, Y, Z.
So remember that 11.7 is extra credit. We're going to cover 11.8. 11.9, I'm going to make 11.9 extra credit also. I don't think we're going to get too much blowback about that. 11.9, the ideas on 11.9 are so rarely used, and it is so very confusing that all I'm going to do is later I'm going to go back and cherry pick the couple of things that we actually need out of that section for later. So you can certainly look through it if you want to try those problems out. Go ahead. They're very archaic formulas. We sometimes see reference to them, but not very often. So if you want to look at that. So today what we're going to do is we're going to do 11.8, and we're going to do part of 12.1. And my plan is actually to let you guys out a little bit early, just to continue misrepresenting myself as a really nice guy. Letting you all see the later tests, yeah, appreciate it now. The thing from 11.8, and the reason I kind of wanted to do this before the last test is it comes right off of an idea I started with when I talked about 11.6. And that is this idea, this very simple idea of if I have something going 30 mile an hour this way, 40 mile an hour that way, how quickly is this changing?
50.
Which is really the distance between the two. I've just turned the diagonal this way. It's changing 50. That's 3, 4, 5 triangle. It's the Pythagorean theorem, right? It's the square root of the rate of change of x plus squared plus the rate of change in y squared. Right? It's just good old Pythagorean theorem. How are we doing? And of course, these are speeds, so that's why I'm calling them the rate of change of my position x and the rate of change of my position y. And I could extend this idea to 3 dimensions, and of course, it would be the same idea. How are we doing so far? So, if I wanted to know after 5 hours, how far apart are these two? I always think of boats when I'm doing this. This is, by the way, a boat. As seen from overhead. It's a canoe with nobody in it, and it's moving itself, so just deal with it. After 5 hours, how far apart would they be?
200.
So you took this, cool. Remember, this is 50, isn't it? This is the 50. It was the square root of 30 squared plus 40 squared. That's how we got 50. How we doing? Good old Pythagorean theorem. Times the change in time, which in this case is 5 hours. That'd be 50 times 5 is 250. 250 miles. All right, you doing okay now? So far? The nice thing is, yeah, go ahead, sir.
I was going to say, wouldn't you multiply 5 hours times each?
You
times
could.
40 and 30 and then get that
You could.
hypotenuse?
You could.
And it comes out to the same exact one?
Yes. So of course we're always going to try to do things the quickest, most efficient way. Because math people are lazy, frugal with their time. What does it look like I'm kind of leading us in what direction with this expression here? What type of calculus idea is going to come into play here possibly? Well, derivatives are already in play. Integration, right? Delta t is going to become dt. I'm going to get a bunch of sums of these things because do these have to necessarily always be constant?
No.
Of course not. I could have functional representations here for how quickly it's moving in the x and the y direction, and the z if you want to get crazy. Right? I'm still going to put them together the same way and then define the distance that actually went. I'm going to integrate this over the change in time. How are we doing so far? So that's hopefully pretty simple. Now, getting into the nitty-gritty math is actually not that hard either. I like this general idea, but the nitty-gritty math, and I'm going to do basically what the book does here. If I have something defined based on t, parameter t. So like this would be x of t1, this would be x of t2. So this would be y of t1, this would be y of t2. Right? So far so good? So if I focus on this piece here, I got this point here, x, y, let me see if I can do this with you guys at t1, and this point here, x, y at t2. You guys okay with that? It's not really accepted, but I don't care. That's the way I'm going to do it. So if I wanted to figure out how long this curve is, which is really what we're trying to do here, we're trying to figure out how long that curve here. Here, this is a very simple problem because the curve was actually a straight line. Right, so the integration there didn't even need to happen. I could just do it directly. No integration required. It's a constant in here. Who cares? Here, what I want to do is I want to find out how long this line is. So I'm going to have to take into account how quickly it's changing with respect to the variable t, with the parameter t. Same idea as here, just more general, because now I have these little functions that describe. This was also a function, but it was just a constant function. Right? How are we doing so far? Semi-decent, okay. So this is the distance I want to get. So here's my delta y, here's my delta x. And the beautiful idea with this is it's pretty straightforward, and it uses the mean value theorem. Who remembers what the hell the mean value theorem is, what it says? Who remembers hearing that phrase, the mean value theorem?
It's like finding the area of the triangle is sort of the midpoint.
It might be used for that, but what's the mean value theorem itself
The
say?
average of the 2 points, there's got to be some derivative, something equal to it somewhere in between.
I like it. So if the function does this, there's got to be at least one place where the slope of this line, this curve, is the same as the slope straight from here to here. So it comes up a Rolle's theorem, which is a specific case where it's 0 to 0, right? Where it starts at this point and ends at the same point. So somewhere in the middle, it's got to have a flat slope. If it's a continuous function, it's not allowed to suddenly go, I want to jump here. You know, that wouldn't be nice if it did. So if I have a continuous function, at some point, at least one point, here I see a few places where it would possibly be parallel to the line that would connect the points as the crow flies, right? Bam. You guys with me? This idea is used so much in integral proofs because of the fact that I'm dealing with a range of t's here, right? I'm dealing with from t1 to t2. When I want to transition to my integral, what's going to happen with the range t1 to t2?
So limits that.
It's going to take the limit as delta t goes to 0, right? That's the idea behind the integral. So if I can say something like at some point in between t1 and t2, at some point in between there, it does this, then if I take it to nothing, I don't have to worry about the specific point anymore. It's just going to be that one point. So let me see if I can, I don't want to do the whole proof necessarily. This is on page 751. So far, here's what where we're at so far. If I add up all of these little things here, and how long is this line here? How long is that line there?
Delta x squared, delta y squared, square root.
Good, square root of delta x squared plus delta y squared. So the length is going to be the sum of the square root delta x squared plus delta y squared So far so good, right? A little bit, all right. What is delta x? Well, what is x itself? What is x?
Function of t.
Function of t. So let's just represent x as f of t. And y, of course, incredibly enough, would be
Function of
g of t, we'll call it. Cool. Right? So delta x, here's where the mean value theorem comes in. Delta x,
It's f
f
of t2 minus f of t1.
yeah, it's all this crap. Let me go right to the point. It would have to be the slope between these all crap and all this crap, and it should be a bunch of crap. The direct way to do it is to realize there's some place in the middle that is parallel to this. So if I just say f prime at that point
Oh.
times delta t, that's where I use mean value theorem. I don't go through the whole slope formula crap. I just say there is a place in here that has the slope that I want. And the beautiful thing about the integral is I'm going to let that range go to nothing. So then which point is this? The only freaking point there is at that point, right? And the limit go to nothing. So it's going to be the only point there. That happens so often in integral proofs. Pick the point that makes it do what you want to. Why? Because at the end it's the only one that you can use. Sweet. Okay, maybe. And now I can pretty much see where this is going to go. I can take out of here I can put it into f prime. And I can take out, I'm going to have a couple of delta t squares. Is that cool? You can see that? So then delta t. And now you take the step that should be very familiar now. The summation becomes the integral. The delta t becomes a dt. Beautiful. So I get the integral dt. And that's how to get the length of an arc. And to make this 3D, you just add plus h prime of t squared. Ooh, right? That would be the function describing z. Yep.
Is it a t sub k or whatever that point is?
Again, from here to here, yeah, right here it is.
Yeah.
You're right. But then from here to here, that's where the whole, I don't care what the k is, it's just the only point I can use at that point. We'll let the limit of the range go to nothing. So that's why it can be just t, whatever it is right at that point.
How do you know what point that is?
Because so again, to go from here to here, each little element here, this is one little element blown up here. The range it can use goes to nothing basically, right? Or if you like, next to nothing. So then how much options do I have for tk? Really just one. If this is in the limit that delta t goes to 0. Tk is in the range, T1 to T2 or whatever the T's are. If I let that range go to nothing, how many options are there for what Tk can be? 1, whatever the T is at that point. Maybe. It's that limiting process that helps me out. This happens so much. It's going to happen to us again at least 2 more times this semester. I'm going to come right back to it and say, remember the whole thing? I can pick whatever makes it work because I'm going to let the limit go to nothing. And then I'm going to have one thing to choose. Right? There's only one thing it could be.
What's that one thing? What's that one thing that it can
The one thing. I love that answer. That's all I can say. The one thing it can be. And again, let me call this, I'm calling it T1 and 2. Let me be more general. Tn and Tn plus 1. So in this example, Tk can be anything from Tn to Tn plus 1.
But you don't know what.
When I take the step to go to the integral, that's the limit as delta t goes to 0, right? Oops. So then how wide is this?
It's not one.
1 wide. It has no width. It has one element. The element is t at that point. So what do I use for t at a point?
T.
That t, right? So this is the idea behind integration. You have crude steps, which then becomes infinitesimally fine steps. So I can make nifty generalizations in the process because this step is going to always make it just the one thing. I'll say, I'm going to choose the thing that works. How do I know it's going to work here? Because then there's only one thing that could be chosen. That's the one that's going to work. I'm always hopeful. So this is the true mathematical analysis, of course, they kind of spell out a little bit more in the book. So you might want to follow up and read through that. But don't forget, the reason that this works, we already did this. We did it with that whole motorboat, one going north, one going east, whichever one it was, I can't remember now. Right? And that was basically, actually, a good proof. If I was a little more precise, would that be a decent proof? This is the real heart of it, going to Riemann sums and all that kind of business. Right? So I want to show you both ways. It ends up being exactly what I would hope. Let's do a concrete example. Concrete examples are always good. Can somebody tell me what that describes geometrically?
Circle.
Circle of radius A. I love it. So if I find the arc length of this circle for t from 0 to 2 pi, what will that also be known as? Circumference. And of course, circumference should be 2 pi r, which in this case would be 2 pi a. So I better come out with that answer, or else we can throw this whole thing away and move to the next section. Right? That would kind of suck because it depends on some of this later. So how do I do this? Well, what's it tell me to do? What's my f of t in this case? A cosine t. So what's f prime?
Negative a cosine t.
Negative a sine t. What's gt? So what's g prime of t?
A cosine t.
I love it. So the length is integral from what to what? To get the whole circle? 0 to 2 pi. And to be a little more specific, why does that get the whole circle? How do I know that gets the whole circle?
It's repeating itself after that.
Yeah, it starts repeating itself after that, and 2 pi is the...
Definition of the...
Careful. It is, but not really. If I would have put a 2t in there instead of just a t, what changes? Starts with a p. Starts with a p. Period. Good. Right? The period of both of these is 2 pi. So of course going from 0 to 2 pi will capture the whole thing. You with me? So if I would have put 2t and 2t in there, what would the period have now been?
0 to pi.
0 to pi. If I would do 0 to 2 pi, I would have gotten 2 circles. I would get 4 pi a as my answer. You guys kind of with me here? So you do have to be careful about how far do you want this to go, especially obviously with periodic things. If it starts to repeat itself at some point, you got to pick what point does it start to repeat itself, right? I walked around the building. I didn't walk 18 miles. I don't want you to count it over and over and over and over and over again, right? Just count it once, and then that's it. So here, what am I going to put in there?
Negative a sine t.
Squared.
Squared. Just remember, it's based on Pythagorean theorem. That's the awesome thing about this. There's the x, there's the y, I want the square root of x squared plus y squared. Well, the prime, the rates of those, right? So here's the x prime squared plus
A cosine t squared.
I was going to write y prime. And of course, this is almost too easy. You get a squared in both, so the a can come out. Cool. And you're left with square root of sine squared plus cosine squared. And of course, this is 1, so you end up with the integral.
No, it's cosine squared 1 is.
Don't worry. Negative goes away. So of course, the integral of 1 from 0 to 2 pi is 2 pi. Cool. Right? So you do get 2 pi a, just like we knew we should. Now what was really nice about that, which if I just made it an ellipse, would make this impossible. Which step up there was really beautiful for a circle that an ellipse could never do? Yeah, what I did right here. Because with an ellipse, what's different? The coefficients would be different. Therefore, you'd end up with something that you could not apply the trig identity to. You'd end up with something really, really disgusting. In fact, I think they talk about it. Oh, let's see. Eventually. Here, on page 754. I love the name of this. It's the complete elliptic interval of the blank kind. It almost sounds like an encounter with alien civilization, right? I always think about the first kind, the second kind, the third kind. And then that movie, The Fourth Kind, I never saw. I didn't want to really see it. But that's just for your own personal enjoyment. So if you're curious, I mean, for example, orbits of planets are actually elliptical. So if I wanted to calculate the true length that a planet traverses, I'd have to do this interval over an ellipse, which comes out to be really disgusting to do. And they have a whole family of them that different software packages can attack. But by hand, I don't want to do that. So I'm not going to do that to you in a test.
We'll frame that up.
That's all there is to it, by the way. I mean, that's this right here. And if I have 3 dimensions, if I would have thrown 3 dimensions at you, you just add in a place for h prime of t. Right? Derivative of the x component, derivative of the y component, derivative of the z component, all squared, square root for the Pythagorean theorem. Bam. Yeah.
So, in terms of the chapter, we're always going to have nice quick identities that can simplify the radical.
I won't say always, but you will have, most of them will. Some of them won't, but they give you relationships that help you through. Yeah. If I remember correctly, I can't remember that's in this section. But yeah, most of them should be something where the trig identity actually boils it down to something you can do. And you can certainly use interval tables. Right? On a test, I'm not really going to let you do it because they normally give you stuff that I think you should know. But in the homework, if you hit a weird one, you could look up to the interval table. I think they have it in the back. Yeah, they have interval tables. If you don't, by the way, if you're going to be an engineer or something, or even a math major, if you don't own some kind of mathematical handbook, get one. They have little pocket editions. I have one that's about this thick with thousands of interval forms. Trust me, I used it a lot in my upper level courses. Forget about it. My physics, whatever, my math, whatever. I used the hell out of that thing. Trust me. Of course, we didn't really have too much internet back then, so I date myself with that. Yeah.
If you add a third dimension to the circumference, then what would be the physical interpretation of
Oh, if I added a third component?
Yeah.
If I add a third component, then I'm talking about possibly a sphere, if I define it correctly, right? It all depends on how that third piece is defined. What function is it based on? I mean, if all I did here was add like a 1 or something, what have I really done? It's still a circle, I just lifted it up by 1. You with me?
Yeah.
So then, what should happen here then? Because of course, what's the derivative of this? 0. So if this is not constant, it all depends on how it's defined. To make it a sphere, there's actually a problem in the homework, I think, that is a sphere. So you can find the surface area of a sphere in 3 dimensions. It's either in the homework or it's in the examples. It's in the homework? Okay. I know it's here somewhere. I can... Oh, too bad. Somewhere near this one.
Flight of an eagle.
No, that one is actually, I think, a helix. Yeah, they got the picture of it. Right, just going up. So that one is a good example of a third component. It's not a constant, but it is a function of t. So what it does is, as t changes, it actually changes the elevation of the function, right? So think about it. If I have a flat circle, so here's the xy plane, here's z, but it's flat. I can find that circumference easily, right? Don't even need this. But if I add the z component and have it start here, but then start to pick up and go a little bit higher and then come here, from overhead, it still looks like this, right? Will the length be different?
Number 18 under basic skills probably is too.
Oh, looks like it. Yeah.
Does it depend on like the period?
So we've seen one like this. It doesn't just pick it up. It actually does like this. So from overhead, it would still look like this. But as it moves, it actually goes up a little bit, and then up a little bit more, and then up, and then it's up here. So it still looks like a circle from above, but of course, once I add that other dimension, it's going to go further, isn't it?
Like a spring.
Like a spring. Thank you. That's the word. You guys kind of with me? So that would be like that eagle flight one. That one they made a little bit easy because it comes out constant. They almost have to do that though. So there's that eagle flight one where R of t, 250 cosine t, 250 sine t, and 100 t. Right, so we've all seen birds do this possibly. They kind of circle, but they're also going up or down or whatever because they get to move in 3 dimensions more often than we all do. But you know what I'm talking about. We can't go up and down very much. So they're going like this. So that's exactly what this describes. 250 cosine, 250 sine is a circle of radius 250. So if the third component wasn't there, it'd just be circling forever. But the third component is there, so every time t changes by 1, it goes up by 100, doesn't it? Cool. So obviously, once I add the third component, the length is going to be longer than it would have been because I've got that third dimension to move in. So try to do that one. What would it look like? Set up the interval.
T from what to what?
Oh, sorry. It's from
Or in 10 minutes.
in 10 minutes. So t goes from 0 to 10.
Thank you.
Not too bad, right? So you just get 250 cosine t, sine t squared plus 250 cosine t squared plus 100 squared, right? The derivatives of each of the components. So the sine squared plus cosine squared goes away because they have the same coefficients. So you end up with the integral of the square root of 250 squared plus 100 squared plus 1. Sorry, from 0 to 10. So whatever the hell number square root of 250 squared plus 100 squared is,
269.26.
you just do what with that to do the integral?
3,000.
But that's not right though, because you pull the 250 out of the equation, and then you're left with sine squared plus cosine squared, which is 1.
Good.
So it'd be
Yeah.
101.
Can you pull two?
No, come on now.
No.
This'll be
It's
250
1.
squared times 1.
Okay.
Yeah, the 1 can't get sucked into that 100 yet. We doing okay with that? Alright, of course it's the integral of the constant, which is just that constant times the range. You guys remember that? I mean, I'm just gonna multiply this by 10. Right? So it'll be, what did you say, 269, 26926 basically, if I remember correctly?
Yeah.
Okay. 0.6. Okay. Yeah.
If we ended up with a integration of like a cosine or sine, we have to break the interval because we will get 0, like from 0 to 2 pi, and we ended up with sine.
You don't have to break up the interval. You don't have to break the interval up like from 0 to some point.
Yeah.
What are you
like
worried
from-
about
from-
happening?
From 0 to pi over 2 to get up the right answer, because otherwise we'll get 0. Like this example here and example 2, page 752.
So on that one, it's because of the fact so example 2. The image, well, the function they give us in example 2 is this. And when you graph it, it looks like that, roughly. Very roughly. So, of course, the problem with cosine is the same problem we would have. The weird thing about this integration, and we don't get deep into it enough yet to realize this, but when I want a true integral, if I want like a true distance gone and I get some integral where it goes dips down, if I want a true area, I have to change the sign of that because I know that it goes below. So of course cosine back here in relation to x and y is negative, but now it's all related to t, so it's really kind of difficult to tell where that kind of transitions. So in this one we realize that it's symmetric, and we break it up and we just get the interval here, and then multiply that by 4, right, to pick up all the way around. Because if I try to integrate it directly the way this is, some of those integrals will cancel with some of the other integrals. So it'll come out negative, just like the integral here would come out negative. Thankfully, that doesn't happen often enough here, because it's not easy always to tease out when that's going to happen, right? Here, let me think about it. Oh, what did it give me? 0 to 2 pi. Let me see if I remember this. They don't talk about the why they have to do what they did, which is kind of evil. Because you're right. I remember this from last semester. I try to tell my students to be careful with this one. They said that they decided to do this just because it was easier and multiply the interval by 4, but it's actually necessary to do that because part of your integration actually cancels out with other parts. Sometimes you learn that by doing the full integral and realizing, oh crap, I got 0 and I shouldn't have, right? So then you go back and you do like they did, you break it down into just one component and multiply that by 4. Yeah?
I remember we used to graph it and see how many times it takes to repeat itself. Is there any way that we can graph that on our calculator and see?
Yeah, you just define it parametrically. X would equal cosine QT. Y would equal sine QT. Have you guys ever used the parametric functions on your calculator?
It has it?
Well, actually, we have it.
Yeah, but I don't think that's the issue here, because I don't think it repeats itself here. That's not part of the problem. In fact, if they define this for me, I really have to stick to this. Right? So if they would have asked me to do this, R of t, a cosine 2t, a sine 2t, t from 0 to 2 pi, am I going to come out with the circumference of a circle? Am I?
Yeah.
Am I?
Zero.
I'm going to come out with the circumference of 2 circles, because I'm going to kind of, but I'm going to do what they asked me to do.
Yeah.
Right? Because maybe this is a bird flying at one circle and then it flew around again. So how far did it go? 2 circles. But that's not part of the issue here. I don't think it repeats itself. Even if it did, though, I still have to do the range that they described for me. Because it could be something that's retracing its steps and it's still going that far. Yeah?
How about the fact that it's not differentiable from 0 to 2 pi?
Not differentiable. Why not?
I mean, there is place.
Oh, this cusp here.
Yeah.
Yeah, that could be a big thing to worry about. The cusp there, though, is defined y and x. I got to think about that because the integral ends up canceling itself out. It doesn't go to infinity or something. So that's not part of the problem. In fact, that's the problem for derivatives, not for integrals. Integrals are not affected in the same way by cusps and sharp corners, right? It's not. If this is the way that the function moves by itself, I don't have to define it piecewise, and integrals are okay with it. Integrals don't really care. It's derivatives that freak out here.
Well, you take the derivative as it approaches that point. Because the derivative is just as it approaches that point. So it's insignificant when you're plugging.
Because you never get to that point.
Because you never actually have to worry about that specific point. It's just a limit.
But I think
of the
that was
entire
your
thing.
concern, possibly, was related to what you're asking about earlier, breaking it up.
Yeah.
I don't know if you're thinking about the derivatives at each
No,
of these
I was
positions being
thinking about
stretched.
breaking out
Okay.
because we will end up with integration of cosine multiplied by sine. So if we use from 0 to 2 pi, we will get 0 because it will be cancelled.
Like,
So-
because then you can tell by the symmetry of the
Yeah.
functions, yeah. So that's another way to do it. Sometimes, like I said, though, sometimes you can't enter a problem and know that it's going to cancel itself out. Especially when you've got it graphed as x and y, and the parameter that it depends on is not, you can't see it. So you're not sure where things are going to start
Yeah.
repeating.
You see, another
But-
thing. Oh, sorry.
Go ahead.
Another thing that I had, you have in parentheses the t 0 to pi over 2. If you just simply slap a 4 in front of that,
Yeah, exactly.
if 4 times that, it's still the same limit. Or it's still the same.
But what they don't address in this example is the good point that if I try, let's try to do this integral. But let's try to do it 0 to 2 pi. So what would it look like inside here? What is the derivative of cosine cubed?
3 negative 3 sine cube.
No, negative 3 cosine squared.
Oh,
So not negative yet.
and minus.
Negative sine.
Times negative sine, cool. So there's your good old chain rule. And what's the derivative of sine cubed? 3 sine squared cosine. So instead of
So
just
you just be derivative of cosine 3 like cube, you said plus, you said equal.
oh no, it's a t. Sorry.
Oh,
I try to make my t's have a little curve at the end. Sometimes they don't curve all the way down. Yeah. So now this integral would look like
Sprint.
negative 3 sine cosine squared t squared plus 3 sine squared cosine squared
You can factor out.
from 0 to 2 pi.
Factor out a 9.
I like it, so
sine
9
squared
comes out.
cosine. And you have a sine squared and a cosine squared in each term.
Well, let's see. We have sine squared, sine squared cosine 4 plus sine 4 cosine squared.
I think we left 3 out. No.
Yeah, it would be a 3
No,
on
three,
that
yeah,
side.
So between these, I think I heard somebody say they both have a sine squared, they both have a cosine squared, right? So you could try to do that. You get 3 integral 0 to 2 pi. Sine squared, cosine squared comes out, so sine, cosine. So if I took a sine squared out of here and a cosine squared, that would be cosine squared left, plus I took a sine squared and a cosine squared, sine squared. That's looking a lot better. How many so far? Yeah, so now I just got integral, and this is actually pretty easy. I think this is it. This is where you notice.
3 or 9?
3, sorry, that was my mistake. So they helped me out that the square root of 9 is 3. This is where I notice that sine and cosine, that sine and cosine are different, are odd and even. So when you multiply them, you get an odd function. But you don't really see 0 to 2 pi. That's not going to affect it. Let me think. Where could you see this is going to be a problem? Well, let's see what we get here. What is the integral? How do I do this? Pretty straightforward integral here, right? Yeah, u sub. So,
Cosine is the derivative of sine.
so if u is sine, the derivative is cosine.
So derivative of u. du.
Du, yeah. So 3 u squared, and u was sine. And of course, sine of 2 pi is 0, and sine of 0 is 0, right? So that is definitely a problem. So that's where you back up and you say, it must have canceled itself out. Because visually I can tell that this is obviously not a length of 0. So that's when I take a step back and I say, break it down to just one piece of it, so I can eliminate all the places where it cancels out. So, I come up with an example of, it's exactly like in the past when you had to be careful about when does it go negative so I can make that positive so I don't cancel stuff out if I want a true area. Right, it's the same problem. The nice thing again, this section does not get deep into this. They're not saying, figure this out on your own. Here you go. You get a 0 answer, go back and figure out what went wrong. No. But in reality, that's what happens with a lot of trig integrals. Is you don't learn it until here, and you go, oh crap, and you've already done a lot of the work, thank God. You just have to change your limits. So here I'll just say, okay, let me go to pi over 2, multiply it by 4, and now sine can handle pi over 2. I've eliminated the parts where the integral is coming out negative. Cool? And again, if I just look at sine itself, if I took the integral from 0 to 2 pi, what happens?
0.
Comes 0, yeah. So and this has a little bit more going on, but if I did take I don't have to actually do this. I could go to pi over 2, but if I went to pi over 4, got the integral there, and then multiplied by 4, that would be the true area, right? Because integrals, of course, sometimes come up with negative area. Depending on your teacher, they call it that or they didn't. But that's what the hell it is. It's freaking negative area. Right, so sometimes when I'm physically working with something, I got to take that part out. We normally do that by changing the limits. Yeah.
Can we just use absolute value instead of multiplying it by 4?
The thing about absolute value is you still have to figure out where it's the same and where it's the negative of it. I mean, it makes it into a piecewise function then, right? I mean, what is the integral of the absolute value of x? Well, it depends on what the limits are, and then I got to figure out which side is which. I mean, it doesn't make it easier, the calculation, actually. Yeah. Okay. Of course, you can slap it into your calculator and it would just eat it up, right? Just put the absolute value function in there and then it should be fine. Okay, how are we doing so far? So again, just to make sure you understand, the issue that comes up with this problem, they didn't even address it directly, which should tell you that it's not going to happen in the homework. The homework should be a lot more straightforward. In fact, this section should be crazy straightforward. Right, you've got the form, L equals the integral of the Pythagorean theorem idea with the rates. Cool. You just have to plug the right stuff in and chug the integral out. Shouldn't be anything terribly evil. There might be some U sub, there might be some even more complicated subs, I don't know, we'll see, yeah. Oh, so let me do this real quick here. Share. Is that okay for you guys?
Yeah.
You guys, share. For some reason they decided not to do that. And then, let me see. Can you show us?